was asked by the organizers to come talk about storing intercrops, and really my answer was there's really not a whole lot we know out there from a research perspective on how we store intercrops, kind of some of the principles that we have for other major commodities. But I said I could come here and talk about our experiences at PAMI and how that could apply to intercrops, what the considerations that we need to look at, and what our future research needs to target as we lead into this. And this applies to both conventional and organic. We've focused a lot on our side, especially in Saskatchewan, looking at the conventional system, trying to incorporate that, but it definitely applies here. Here we go. So there's an old article, I think it was 2013, Grain News, talked about six things to consider when intercropping. So it's crop choice, seeding, fertility, spraying, harvest, and rotation. But what about separation and storage? So that's where PAMI started to look into. So I'm going to talk about why would we store intercrops, basic principles of grain storage and drying, kind of overall principles, some potential storage issues, and tools for managing. So separation, is it necessary? Can seed be stored mixed, or does it need to be separated? Well, really there's not a whole lot of markets for intercrops, particularly in the conventional systems, so it does need to be separated eventually. Requires financial investment and time investment. So handling logistics during a busy harvest, this isn't always the most, you don't want to necessarily be adding an extra step, so sometimes you do have to store. So is there a workaround? Can mixed crops be stored until there's time for resources? Time and resources are available to separate? Or in thinking of risk management, if I have to store intercrops until I have time to separate them, how can I make sure that they're safe from spoilage? So like any storage of grains, what's our potential issue? Hot or wet grain can spoil during storage, and of course spoilage means lost revenue. Risk of spoilage depends on both temperature and moisture. So these are things we gotta manage both. We can't just cool our grain and expect it to be good, it's gotta be dry as well. But the rate of absorption or desorption, so whether it dries down or takes on water, is crop dependent. So when you start talking about a mixed crop, this becomes confusing because you have two different crops that behave differently, and how do you manage them at the same time? So our main commodities, so of course in mixed crops we're going to start to get into specialty crops, but I'm going to kind of focus on available information that we have for key commodities. So example, a pea canola type mixed crops. We've got safe storage conditions available for each of those monocrop commodities that tell, based on the seed moisture and temperature, when those would be safe to dry, or safe to store. So how do we manage moisture and temperature? This is regardless of what we're storing. So a little terminology, when we're talking about aeration, that's just temperature control, low airflow rates on our bins, and just keep our grain cool. And then we look at natural air drying, or NAD, and that's how we use to dry our grain. Higher airflow rates, and if the air has the capacity to dry, it will. But managing these different practices requires knowledge of our optimization of, the key ones are resistance to airflow. So this determines that you're achieving the airflow you want, and uniformity of that airflow to make sure you're drying or conditioning your bin uniformly. And how the external and internal bin air conditions will affect the grain. So I said it, airflow rate, which defines how your management practice depends on resistance to airflow. So, and resistance to airflow depends on grain type, so it's the size of the voids. So our main commodities, we have an idea of how air flows through those, but as soon as you start introducing two grains, you have the smaller grains, say canola, filling in those voids between the pea, larger pea pores. Depth of grain, airflow rate, the faster you blow air through, and distribution system also factor into that. But in the case of mixed crops, it's really that void. So these are the charts that are available for the monocrop commodities that you can use based, if you can measure your airflow resistance and how deep your grain is, you can know what type of strategy you're looking at. Yeah. And kind of just a basics, this regardless of what you're storing can be for your basic organic monocrops. So there's tools to use to measure these principles so that you know, or measure your resistance so you can work with your strategies effectively. So airflow resistance gauges, static pressure at your fans, and different online tools from a University of Minnesota app. So I said that these are commodity specific. So we have peas here and oats here. The vertical axis here is the same scale, but the horizontal axis is a little different. So we can see that the resistance through canola, which we expect, would be a lot higher because small seeds, small pore size, harder to push air through it, whereas the peas you can push through fairly easy, low resistance. So we really don't know what the difference is, or when you combine them together, what does that look like? We're probably better to err on the side of the canola. And then another thing that kind of goes on top of this is, what about size segregation in the bin? So as you're filling the bin, do those smaller seeds, do they distribute evenly? Like, so do you have a uniform mix throughout the entire bin, or do they kind of tend to congregate in a single area? So this was just a really quick model that we put together, but you could see potentially, depending on how you fill your bin, that you have those small particles on one side, and all your peas, for example, taking up the rest of the bin, and air will flow through the space of least resistance. So you won't get airflow moving through that higher resistance mixed crop portion. So those layers and areas of concentration, poor uniformity, like I mentioned. So localized areas of increased resistance and preferential airflow through low resistance. And if there's a pocket of grain that has a higher moisture content, and you can't, so say that your canola's a lot higher moisture, but the airflow is not getting to it, then that could cause some problems. So then we talk about moisture migration in a bin, and if we have to dry, or what conditions, how does moisture move through the bin? Even if, for say, both grains are considered dry as a monocrop. So we use these EMC charts for our main commodities, and some of our specialty crops can be extrapolated from those, pick a similar crop. But they're used to determine how your outside air will affect the grain moisture, and how that grain moisture will affect the air conditions within the grain bulk. So we compare our humidity of our outside air and our temperature. And so if we look at charts for both peas and canola, we see that if we're at 70% humidity and 22 degrees Celsius, for peas, we're gonna reach an equilibrium moisture content. It's gonna baseline over time to 16%, whereas in canola, 9.3. So it's different for each commodity again. So kind of some scenarios for peas and canola. So the air within the grain bulk will eventually equalize to to certain humidity, like certain moisture contents in the air around the kernels, depending on what the starting moisture content of the grain is. So if we put our dry peas and our dry canola based on safe storage dry for those two monocrops, when we've got lower temperatures, 5 to 15 degrees, that humidity of the air surrounding those kernels is very similar. So the green values are a small difference between the equalizing air moisture within the bin. But the larger that difference is when they equilibrate, the bigger potential problem is for moisture to migrate from one commodity to the other. So we see, so kind of that's a summary of there. And kind of a synopsis is for pea canola, if both are dry, they should be okay, like I saw there. So there's our green value. Both should be okay, shouldn't have moisture migration through the bin. But we could have issues if peas are dry and canola is tough. Yeah, so that's this situation here. And then another one we've looked at that is a complicated one is flax and lentils. So there's a big differences in equilibrium moisture for those, and the only scenario that works from that approach is dry flax mixed with tough lentils. You won't see moisture migration, but that only minimizes the potential for migration. But the lentils are still tough and the risk for spoilage. So that's where it starts to become really complex. So really that doesn't answer a whole lot of questions. And our recommendations really are to monitor your bins as much as you possibly can. With the information we don't have right now, you can get an idea of which commodities might be safe to store based on how they interact as a monocrop. But really, if you have the ability to monitor your situation in the bin, that'll give you your best risk management insurance to be able to react if it starts to potentially spoil. So those are just examples, but so the thing is, moisture sensors are based on those EMC charts, so they might be not effective for intercrops, but temperature cables will be able to identify hot spots, so that's probably the better option. Oh, that's the same comment, I guess. And once again, when you're setting up your monitoring, that sensors, there's limitations to them, how much you can see in your bin. If you've got small bins, that's not as big of an issue. That's just another example of a monitoring system. I put these in most of my presentations. Potentially, this kind of applies to the organic and mixed crop situation and adding to an element of traceability is using small sensors put into a bin is another emerging technology for how to manage conditions in the bin. It doesn't just have to be temperature and moisture. So really it comes down to what don't we know about storing intercrops and what do we need to learn more to be able to manage effectively. So we don't know the safe storage conditions for all combinations of interest, but we think we have a way to figure that out. The airflow resistance for various combinations of intercrops, we don't have that information. We can speculate based on the smallest particle, or smallest kernel size in the meantime. How much does size segregation, so I showed that model of the smaller kernels pooling in one spot, but is that really what's happening or are we overestimating? So taking a look at that a little further. And from the point of moisture migration, we know that certain kernels, certain commodities don't give up moisture as much, so maybe moisture migration isn't as big of an issue. So those are things that we still have to find out, but they're discussion points to keep in mind when deciding whether to you can store your grain. And so hopefully we're going to be, PAMI is working on trying to start to answer those questions as intercropping becomes more of an interest. And just kind of a segue, I included this this next little bit of a section in segueing into the next panel, because we were talking about how to manage our crops in challenging harvest situations. And this is a talk I've been giving quite a bit over the last year with the fall we had. With snow in the fall, cold weather conditions, not ideal situations for storing grain safely. So just gonna fly through this and then we can jump into the panel. So we all know we had a challenging harvest. We look at ideal conditions where we can dry grain in bin and it's safe to store. By about 10 degrees Celsius is the turning point of going from good conditions to not ideal. So typically that happens based on our average temperatures in Manitoba in early October. And if we look at how much was harvested in early October, or by October 1st, on average we're usually around close to that 80%, but this year we were well below 70. So a lot more grain that has to be handled and managed carefully before we put it in a bin. So earlier I mentioned, when I was talking about natural air drying, just briefly touched on it, was air's capacity to dry. So this talks about air and how much moisture it can take up, which implies whether it's going to dry your grain or not. So if we consider the analogy of a glass that we fill with water, warm air would be a large, tall glass, and at 60% RH, we've got a fair amount of room that we can fill up. But then if we consider colder air as a small glass, if we've got 60% humidity, it's still the same RH, but the amount of water from a volume perspective is a lot lower. So that space is how much water it can take up. So warm air has a greater capacity to take up air away from the grain. And if we look at these charts, so when air has a capacity to dry, so if we look at our humidity and our temperature, and at 70% and 10 degrees Celsius, 15.7% is not considered dry. For wheat, we want it down below 14.5. So really we're looking at air conditions that result in these moisture contents. I don't have this range highlighted because we've learned that temperatures below 10 degrees Celsius really make for inefficient drying. So how do we extend the drying season? So we want conditions to be above 10 degrees Celsius and 70%, which we know definitely wasn't happening in late fall here. But we can use supplemental heating on our in-bin systems to extend that drying season. And our rule of thumb for this, and it applies to any grain that you're storing, is for every 10 degrees Celsius in air temperature that you increase, the humidity of the air is cut in half. So if we had a 70% humidity and 5 degrees, so not an ideal situation, if we can add a heater to our fans, we now are able to dry it down to safe storage conditions fairly easily. The key that we stress, and this is primarily on really storing large volumes of grain that it starts to come into consideration, that we really stress, is that supplemental heat is not the same as heated air dryings. So using a dryer so that uses high temperatures, high airflow rates. If we're using it in the bin, we want to match how much heat we're adding, which is drawing the moisture out of the kernel, to have the airflow rate to make sure we move it out of the bin and we're not just pooling water somewhere else. So there's different, I'm going to skip through this a little bit, just kind of an overview though. Different ways of adding heat to a fan, indirect, direct, upstream, downstream, different advantages, disadvantages to each. We've got a fact sheet on our website for this information if you want to know more about it. Equation for how to calculate how much heat you may want to add to draw out as much water as you want. Example of that calculation, making sure to account for losses and efficiency, depending on what system you have set up. We've done quite a bit of work on efficiencies of different drying systems, or we're working on that to help add more information. Cost of grain drying, so depending on what fuel type, that definitely plays into it. This is one to look into, or to make a point of, is natural air drying with using supplemental heat can be a lower capital option to a heated batch or a batch or continuous dryer to reduce with reduced operating costs, but only if it's managed effectively. So you have to understand what your parameters are and use the principles to make sure you're drying efficiently. Because if you don't, and it takes a lot longer than your realistic costs, operating costs become higher. So just, these are what I wanted to get to. Guidelines, if you're gonna use supplemental heat, make sure you use a certified heater. There's lots of redneck setups out there that are being used, but there's no point adding heat to dry your grain down to reduce spoilage if you're gonna set it on fire. Adequate airflow rates, so that's make sure you're getting the moisture right out of the bin. 20 degrees Celsius is what we kind of aim for ideal drying conditions, as long as you have a 1 CFM per bushel airflow rate. That rule of thumb, 10 degrees increase in temperature cuts your AH in half. And then you want to cool your grain after you dry it. And monitoring is really the key. So this is our PAMI website, has some of those charts, so they can be used as a starting point, and there's some FAQs inside of some worksheets for working through those situations. So we don't have all that information for mixed crops or some of your specialty crops, but we can start to kind of fill in the picture and use those guidelines as guiding principles to go on. So that's kind of all I have right here. Not a whole lot of information, but hopefully it provides some a start of discussion and